Welcome back everyone for part 2 of using the divergence test. Last time we were able to show how a series diverges using the divergence test. This time we're going to look at another series and show how we can use the divergence test when it doesn't show that the series diverges. So let's get at it. Alright, so I kind of have the definition still written out from the last example that we did, and let's just kind of recap what the definition says. So if we have a series going from 1 to infinity of a of n, so a of n is just a function of n, we're going to take the limit of a of n as n approaches infinity, and if we can get that to not equal 0, then we know that the series diverges. Okay, so let's take a look at how that's going to work on this example here. So if I identify my pieces, so our first thing is to identify that this is our a of n, and then what we're going to do is we're going to go ahead and plug that into our limit. So the limit as n approaches infinity of a of n, so let's go ahead and plug that in. Limit as n approaches infinity, looks like it's going to be 2n plus 3 divided by 3n squared plus 5n plus 2. Okay, so kind of like the last one that we did, we're going to go ahead and multiply this by 1 over n squared to both the top and bottom. Okay, and then let's simplify. So the limit as n approaches infinity. When I distribute that through, it looks like I'm going to be left with a 2 over n plus 3 over n squared divided by a 3 plus 5 over n plus 2 over n squared. Okay, and so we're going to go ahead and plug in our infinity. So when I plug that in for n for these two, both of these ones are going to go to 0 because our denominator for both of those fractions is getting really big. And then this one's also going to go to 0, and then this one's also going to go to 0 as well. Okay, so let's see what we're left with. So it looks like we're going to be left with a 0 on the numerator and a 3 in the denominator, which this is just going to be 0. So let's kind of take a look at what that means. So if we look at our definition again, we wanted to show that it does not equal the function a of n as n goes to infinity does not equal 0. And then that tells us that the series would diverge. However, we showed that it does equal 0. So what this means is that we're just going to need to do further testing to see whether the series converges or diverges, and that the n-term test for divergence for particularly this series is inconclusive. So kind of last couple things to remember is that you can never tell if a series converges using the n-term test for divergence, and that even if a series doesn't diverge through the n-term test for divergence, it may still diverge using a different test, a different series test. All right, well, thank you guys for watching this video.